Yeah, hi. So, hi everyone. Good evening. So, this is the second session of this week. So, I have some plan for some experiment on the board. If you have any query before that, you can ask Ro, Mathili.
You can start, sir.
Okay, okay. Sure. Yeah, Dhruv, do you have any query? You are not audible. I think you are turning on your mic, but your voice is not coming. Please check your mic once. Okay, now Vinas is joined. Sir, I asked one question on this course. Oh, okay, let me check. Programming C where natural lab session. Okay, this is embedded C. Doubt is now evaluation B3 recording error sending to the doubt in quiz one paper. Okay. Okay, so let me copy this. So I'm sharing my screen first. One second. Okay, so I think this is your doubt, Dhuru. Uh, yeah, Dhuru, you are. Let me copy this. So I think we have discussed these things in C course as well. Also, I think some assignment question is also there in the weekly assignment. Okay, can you check your mic? Otherwise, I am not able to communicate. I don't know what you have checked out. Okay, so this is based on the typecast based question where we want to convert a one type of value into another type of value. Okay, so when we convert this one type to another type, that is called as a typecasting. So similar for the pointer case also. Okay, if we have one type of pointer and we want to convert to that pointer into another type of pointer. Okay, so you know that we use this type pointer. So like if you want to store that int pointer for the integer element. Okay, so that pointer is called as integer pointer. Another here what is given that which of the following typecast is needed to assign a void pointer. Okay, so void pointer we have, that means that contain a null value, we can say that that is that not contain anything. Okay, so to an integer pointer p. Okay, so we want to convert this using the typecasting. So typecasting is simple. If we have pointer p, that is a integer pointer. So here the way of the typecasting, uh, so if we go option by option, so this option actually. Okay, here this v value is the direct pointer. Okay, so that is fine. uh, but here this is the integer, so this is not the correct because this is a integer typecasting, not a integer pointer typecasting. So this is like suppose if you want to convert any float value, so like we have float and a equal to 2.2.6, like okay, if we have suppose this type of value float a and we want to convert that value into a integer value, so how we can convert? So int like b equal to, then we will use the typecast int. Okay, and we will use this variable a here like this. So this is called as a that integer variable, not a pointer. This is not a pointer typecast. This is an integer typecast. This is converting this a value, which is actually a float, into an integer value. So this option is incorrect. Another is the second option. So second option, Here actually, yeah, okay. So this v is a pointer. Okay. So okay, so one second. Yeah, so this end, yeah, and what we are doing, which of the following typecast is needed to assign a void pointer to an integer pointer p in C? Okay, so these two options are actually confusing. And let's move to this v. So this is definitely not correct because here we are typecasting into void pointer. Okay, so these way of conversion are correct. So actually these three options, int asterisk, and void asterisk, all these are the correct syntax in C. But this void is, we are not converting that v into the same pointer. So this is not correct. Option last. Now option B and C. So these are the two options where we have to think. Here we are converting a that we are not converting a address of v. We are converting a pointer v. So that means we will convert what this is returning. This is returning a like we have a pointer v. Okay, so pointer v means this is a one variable. Okay, and that contain the memory space, and that contains some address here. Okay, so that address is a that void data type. Okay, so some data we have, and that is also a address. So this is also a address. This is also a address, but this address is actually related to a void pointer. Okay, now this void v is actually a pointer variable for this address. Now this is there is some one more address we have for this memory location. Okay, so actually this is a memory locations that contain the address as a data, but this memory location also have some address. So that address is actually for v. So where the memory that address for v, so that we are getting here, and v. Okay, so this is converting a the point that address of v, and this is converting a value of v. Okay, so what is the value inside that? That address will be converted into a pointer address. So here I think this third option should be correct.
Sir, answer is third option.
Third, na? Yes, because we are simply identifying that void integer v to integer pointer p. So we are not saying that the address of v. We are just we are converting a pointer v. So that means the address of this v. So this is not correct, and this is correct. And this type of typecasting actually very useful in our embedded C programming when we are writing a code on the hardware and based on the register level coding. So you should know we can directly write a address in hexadecimal, and then when we can convert that address into a some integer pointer like this without capturing the address by the variable. Okay.
Sir, basically, what is the bracket doing? Can you explain?
Sorry, what is bracket?
Yes, sir. Sir, what is bracket doing?
So
Like,
this
is
is the
it
identity. This is the identification that in what type we are converting actually. In this example, you can see this bracket is indicating that we are converting the value of a into integer. Okay, so this is the meaning of typecast. Same thing here, we are converting a value of v into int asterisk. So this int asterisk means pointer of integer data type. So that value of v will be converted into a pointer of integer data type. So that pointer, after converting this, that value will be assigned to pointer p. So this is the indication of in what type we are converting the current data.
sir, value in itself will become address in integer?
Yes, yes. So that v is also a pointer, no? So this void pointer v, this is also a pointer. If this is a pointer, that means it contains the address. Okay, and that address is converting into a integer address. Okay, so here address we are converting into another type of address. Okay,
Yes.
so this is called as a typecasting. And suppose what we can do in we have discussed in the previous my session. So suppose we want to store some pointer address. So like we have integer pointer and p, and we don't know the variable actually, and we know the direct address. Suppose we have the direct address in hexadecimal form, so like 1354a 622c, like this. Okay, so how we can assign this direct address to this pointer, integer pointer p? Okay, so what we can do, we can do the typecasting. So how will do the typecasting? We will just use this symbol int asterisk here. So now this value, okay, so this is a direct value. This is not a variable, this is direct value. That value will be converted into a pointer address. So that will be converted into a address, and that address will be assigned to a p. Okay.
Sir, and if we write int x asterisk,
This is not a int x, this is a int asterisk.
okay, it's an asterisk. Okay, sir.
What
Got
you are
it.
saying? If you want to write,
Got it, sir. Sir, I thought it was x. X
no, no, no. This
asterisk.
is not a x. This is a asterisk. So I think in the syntax it is. No, this is asterisk. Where it is x? X have only four. Order, but this is asterisk. Okay. And I think we have discussed this type of question in assignment also, and I think B2 programming question also we have discussed this. This is not a new, and C course we have also discussed this typecasting. This because of that we gave this question in the exam. Okay, is it clear?
Yes, sir.
Okay, fine. Okay, any other query? Others? Okay. So, okay, today I have also some experiment on the board, and I have two experiment. So let me just tell you. And yeah, so Beak 7 actually, I think there is no content in the Beak 7, but you will get the programming assignments. Okay. So yeah, because of that, again discussing this experiment on the board, so you will get some idea. So we have two experiment today. So one is turn on off LED by push pull button. Okay, or we can see that instead of push pull button, we can take that input. Second experiment we have is a that adjust brightness of LED by PWM. Okay, so these two experiment uh, I have planned to explain today on the board itself, Nucleo board. Okay, so I have this Nucleo board. Last time I have discussed on the discovery boards. Okay, so you, I think most of you are using this Nucleo board on the walkv platform as well also. Okay, so because of that, now I have Nucleo board. So first, let's discuss this first experiment: turn on off LED by push pull button. Okay, so let me open, and what we need to do this. Okay, so I have this QID. You know that QID. This is the some another example. Let me close this. Hmm. Okay, so this is the QID, and I have also connected my board. So let you show you. Okay, so I hope you can see. Mhm. Okay, so yeah, this is the board. I hope, I'm not sure this is very clear or not image. but I think this is due to network width and width. Yeah, so this is nucleo board. I have one breadboard also, and I have some connectors that connectors, and I have one LED. Okay, so these are the hardware I have today, and this is already connected to my computer and nucleo board, and this is looks like this. So board, I am just showing you. So this is the board structure. Okay, uh, I'm not sure this is visible completely or not. So this is the board structure we have, and I have this model. So this nucleo Geo4 74RE. So this is the pin connection. So you can see. Okay, and we want to write the code on that for the both experiment. So now I have opened this uh, that IDE, that STM32Cube IDE. Let's create a new project, and we will write a code for that. First, turning on or off LED by the push pull button. So let me start new project. Okay, so new, and select STM32 project. So it asks actually this board selector. So I have the board actually. So I'll click on this board, and after that board, I'll select the board which I have. So that nucleo, oh sorry, nucleo. This is the one, and G and 7 for RA. Okay. So when I click on this, I select this board, and after that I can next. Okay, so next, when we are clicking on this next button, it is asking the project name. So we will give a project name. So like nucleo LED by push button. Okay. Okay. So after that, yeah, last option I am selecting this empty. Okay, target project type empty. So we will start from scratch, and there are multiple way to write the code. Okay, so there is one hardware abstract layer, that API we have in this IDE. So where we can write the code without knowing all the details of the hardware, but we will write a code directly on the register level. Okay, so I am clicking on this empty. If I select this previous option, then it creates a some pre-configuration for the project, and we can configure all the project by the manual things. So but we don't want to this, so I am just starting from the empty project. So let me open this, finish. Okay, so clicking on this next. Yeah, so now this is open nucleo LED post button. After opening this, just go inside this src and main.c. Okay, so when you click on this main.c, this file is open. Okay, and now I'm removing this part. Removing this part, I'll comment also. Okay, so this is the fresh page. So now we will write the code. So what we need to find out here, so we need two documents here. One is this user manual, okay, user manual, and another is this that reference manual. Okay, so this is actually for nucleo series. So you can see this is STM G4 series, and same for the user manual. So this G4 nucleo board. So we will refer these documents for the information of the registers and other things. So first thing, now we have this board. So in this board, actually, these pins, that circuit diagram, actually, this pin is given like as a pin name of the microcontroller. That microcontroller is that what microcontroller we are using in this. So that ARM, that microprocessor. No? So that pin is representing to that pin. This is not representing the that our actual board pin. Okay, so this naming is actually different, but we need some more different naming for the pin. So like that is actually represent the that port and that name. Okay, so on this page 29, we have this type of mapping, so where we can figure out the actual port details, all these things. Okay, this one. So you can see the on the board this blue color naming is given. So like this A0, A4, A4, A1 on the board, every pin have this blue color naming. But we need to identify the this port details. So this PA0. So this is represent like port A0 pin, port A1 pin. Okay. Similar on the right side, if you can see D8 is representing like a PA9. So this is PA9 is representing a port A9th pin. So in this way, this pin name is actually given according to the that Arduino board related. So you can see blue is representing Arduino Uno. Okay. So but we want to use the pin of STM micro controller pin name. Okay. So because of that, we will follow this black or black one pin number. So you can see this mapping on this page, because on the board also this Arduino Uno based pin number is given. So we cannot identify the actual board, that actual port, um, with the help of these. Okay, directly. So we will follow this mapping, and we will use this black pin names. Okay, so that is representing a STM. And now this is the things. Now I'll connect this uh, LED. Okay, so I am connecting this LED. One thing we need one LED. That LED actually can handle 5 volt. So we are directly using this. Otherwise, if it's not, if cannot handle this 5 volt, then we have generally use the registers for that. So I'm connecting this on the breadboard. Okay. Now I'm connect this lower that negative. Okay, so that pin into the ground in our board. So that ground pin is actually a, you can see that GND is mentioned on the board on the right side. Okay, so I'm just making a pen, then you can see. Okay, so on the board you can see this one. So this is a ground on the both pin. So we will connect this ground in our board, and this is the fourth pin from the above. So I'm connecting this 1 2 3 4, yeah, and high pin. So okay, like this. So yeah, it is connected. Okay, so let me just take that D8 pin. Okay, so D8 pin is representing PA9. So that pin as a output pin for this. Okay, so I'm connecting that as a positive terminal of the LED. So this is just a connection of with the LED. I have connected one wire with the ground and another wire for the D8. So this D8 is this one. Okay, this one D8, and corresponding STM pin name is PA9. Okay, so this is the PA9. So we will use this pin as a output. Okay, for the LED. Another things, we will use a push, that push button which is already given in the board. If you can see the board on the above, that hmm. Okay, so this blue pin is actually a push button for the user. You can see this is for the user, and this is connected with this V in. Okay, this pin directly V in. So we can directly use this pin, and we can press this push pull button for to give the input. If we press this button, so one input will be passed to this V in pin. If we leave this, then 0 will be passed to this V in. So this pin, or you can also use external push pull button. If we have already in board, we will use this. Okay, so you can see we have connected this GND in this board, and we have used this G8 D8. Okay, now this is the requirement of our connection. So now I'm moving to that 29 page. So you can see V in is a, this V in is a corresponding PC8. Okay, PC8 means port C13 pin. Okay, so we need this information. So that means we need this PA9 port A, that is GPIO port. Okay, so general purpose input output that pin. So port A, and this is ground, so there is nothing to do with this ground. And now this is input pin. We will use this as an input pin, PC13. So now what we need to require to write the code. So first thing, we need a clock register address. Okay, so what are the first things? So require clock registers. Okay, address for RCC. Okay, and second thing is we need GPIO mode A. Okay, so GPIO port A. So GPIO A, and we will find out the base address for this. Okay, so base address for this port, A port. Okay, same. So this we are using as a output. So PA9, we have this pin PA9, and that is we are using for the output. And GPIO C. Okay, this is the another port we are using, which is so base address we will calculate for this base address, and we are using the PC13 for the input pin. Okay, this is a push pull button basically. This is already given in the user board. So now we will figure out the base address for this GPIO A and clock register address, GPIO C base address. After that, we will use this as a output. We will use this pin as a input. So that means output register and input register we also need for this port. So these information I need. So what we can do, we can start the coding. And for this, what we can do, we can define. Okay, so we can define this pointer as a macro. So let me define the thing. So here define, and first thing RCC register. Okay, so RCC registers address, and this that clock. So okay, so this RCC clock is basically connected to the AHV1 bus. So that AHV, there are multiple bus are there, and in both this is connected to the AHV1. Okay, so that I'm just writing this RCC enable. Okay, so we want to enable this clock, so which are connected to a our at port A and port C. So enable register, so ENR. Okay, and what is the corresponding address for this? So we will convert like that, a asterisk and then int asterisk. So this is typecasting I am doing, and we are simply assigning the value. So we will write some address. Okay, so for this, so this is 0x and 00, sorry, 0 0 0 0 0 0 0 0 0. I'm writing randomly value, but we will change this. So this is the first RCC enable register that we have. After that, so we are just not equal to here. Okay, so we will use this equal. So this is a macro. We will use this name, and this when we will write this name, it will be considered as this value. Okay, in our code. We will not write the complete that address every time. So we are giving some naming to understand the code better later. Okay, so define, and now second is GPIO-A. So GPIO-A. This is port A, and we want to that enable this mode. So mode and EN or ER. So mode register. Okay, same things we will write some value for this base address here, and after that, so we will write the same things for the C port. So GPIO port C. Okay, so now this is the mode address. We will select this port and corresponding pin for a input output, what purpose actually we want to use this. And after that, because we are that updating the mode for this, then we will also read the input and write the output on some place. So that address we also require. So that means like this. So again we will define another address. So this is GPIO A, and this A pin we are using as a output pin. So I am writing ODR, output data register. Okay, and port C pin we will use as a input from the push port. So that I am writing as a GPIO port C IDR. Okay, input data register. So now these are the value we need from the documents. So RCC enable register. So where from we can find out this? So let's open this document, that reference manual, and inside this document we will check the memory organization, and we can find out the base address for this. So when we click this, you can see we are getting this memory mapped address, and inside this document you can see the base address for RCC, this one. Okay, so this address is given, base address is given here. Okay, now this one. So let's copy this and write into our code. So base address. I'm writing the base address, but we will figure out so which actually port we want to. Okay, so we have to figure out the that AHV1, that. Okay. So this is the base address of the RCC, and after that we will check the remaining details. Like we will move to this RCC file, reset and clock control. Okay, so here when we click on this, there is option registers. So registers, when we move into this, so we will check this. Okay, so okay, HP1 peripheral clock. So our peripherals are connected with AHV2. Okay, so AHV2, and we will open this. You can see the offset address. So this 4C address are uh, given, and how we know that this our peripherals are connected, so that we can see from the memory again. So let me open this. So where you are connected, you can see. Yeah, so GPIO A, GPIO, all these port actually are connected between this AHV2 bus. Okay, so because of that we are just selecting this AHV2 clock and registers, then AHV2 peripheral so this is not. Where is the enable registers? Yeah, AHV1, AHV2. So AHV2 peripheral clock enable registers. This one. Okay. So offset value is given 4C. So that means we will add this value into the base RCC address 4C. Okay. And here these are the bits that we need to set to enable the clock. Okay, for the working of the. Otherwise, if you skip this, if you are not enabling the clock, your that board will not work. Okay, so this port will not work. So you have to first enabling the clock for the particular board. If you want to enable the board, that port A, for clock for port A, you have to set this bit as a 1. As similarly, we want to enable the clock for port C, so we have to enable this third bit also as a 1. So 101, that means we need to do this. So now this is the requirement. So let's first thing we will change this to 4C. 4C. Yes, someone is raising the hand.
Sir, can you show that figure B? That
Which
manual.
which one? This one.
Sir, here from 7 to 12 bit, why is this empty?
Because we don't have any pin. That means we have don't have any. So we always not use the every bit. Okay. So registers, each registers have 32 bits, but according to our needs we only use that bits. So here some specific bits are given. So like this, these are reserve bit. 30, 27 to 31 are reserve, and similarly this 25 bit is reserved. So all these bits are reserved actually. Those who are not okay are using. So these is this 20 to 23 is reserved. So this is just a specification of the board. So if yeah, this is the only bits which are actually currently using, we are using. Okay, so here port, this is the first six bit we are required. So another is like ADC, so the analog digital converter maybe. So if we want to enable this peripheral, so we can use this DAC. digital to analog converter. Okay, so we have different type of peripherals, and we can enable that peripheral. So this board maybe contain less number of peripherals, so because of that we are not using the all bits, but maybe advanced microcontroller board may contain the large number of peripherals, so at that time that bits are actually used. Okay, so what is the base address will become this 4C, so we will add this 4C in our base address of RCC, and after that we need to make this first and third, okay, that bit as a 1 to enable the clock for port A and port C. So this is the first things, we will do this later, and after that we will find out this GPIOA. Okay, so GPIOA mode register, what is the base address for GPIOA? So let's open again, so this GPIO register, so let's open this general purpose input output. Okay, inside this just open the registers and click on the first. So that means the address. Okay, so here we are not getting the base address, so for base address we have opened the same table. Yeah, this one. Okay, so GPIO, you can see the what is the starting address, so this one. Okay, 4800, this one. This is for GPIO A. Same things we will capture from C. Okay, so let me copy this first. So this is the base address for this port A. Okay, now port C we have the starting address, this one. Okay, 4800, this is the registered address. So we will update this port C mode register. Okay, so 4 is also there. 480, yeah, fine. Okay, so now this is the base address of mode register, and now in this document, when we move to the registered page, so that is registered, and when we click on the first, so this is a port mode register. So this means the base address of the port is also will be also be used as a this GPIO port mode registers, because the offset is 00. And in this you can see, so port A actually we want to use as a output pin. So for output you can see what value should we have, so that is actually port 9. Okay, so we have mentioned this in here, so this is PA9, and 9 means you can see this mode 9, this value, so that means the bit 18 and 19th should be set according as a output bit. So output bit is a 01, so that means the bit 19 should be 0 and 18 should be 1 to set this as a output mode. Okay, port A and pin number 9. So this two bits should be set as a 01 for this. And another, so here what is the offset for this? Yeah, this is the mode register. Similarly, for the C, we want to enable C as a input. So port C, this is also same. No, this is yeah, okay. So port C, we will use the base address of port C, but offset is again 0. So we will use the pin number 13. So pin number 13 is this one, mode this one. Okay, 27 and 26. That pin we will configure as a input pin mode 00. So this is our two requirement to update this. So after that we need two more register, so that is for, so one is the output data register for port A. So output data registers we will get in the same list. You can see input data register, so this is for input PC13. Okay, so PC13 pin, the offset is 10. Okay, and we will use this pin as a input. So you can see we will use this 13 pin, so 13 pin is this 13 number, and if we pass the one value, so that will be read as a one high input and low. Okay, so we will set this accordingly. Now the offset is 10, so we will use this offset for port C. So that is one more address required we have. So port C we have the base address, and we will add 10 in this. Okay, so 810, and that GPIO as a output register. So output register, we have this second next one. Offset is 14. Okay, so same pin we will use as a that ninth pin. So we will use as a output pin. So offset is 14 in the port A base address. So we will add this into this one. Okay, so this is the base address for port A, and we will assign this here, and we will update this by 14. Okay, now all the base address are set, and we will use this name for the uh, in our code directly. Okay, and that will be considered as a pointer. So now comes to the next things. So what we will do after that, first our first work is we will enable the clock. Okay, so let me just write the comment, enable the RCC for both port A. Okay, so here what is the base address? So this is RCC INR. So we will use this address here, and we will use the OR operation. Okay, and OR operation with, and what we will do, so we need to set RCC. So we have already seen that which bit we need to set first and third. Okay, so for the clock, that RCC, and that GPIO register, not this. Yeah, GPIO port will. What is open? So sorry, this one. So this AHP2, 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 AHP1, AHP2. So you can see we need to set this first pin as a 1, and we need to set this as a second one. Okay, so this is for port C and this is for port A. So what we can do, we can so what is the current value of this register, and we will perform the OR operation between 101. So 101 is 5 in decimal. So what we can do, we can directly configure the OR operation with 5 this. Okay, so let me write this 1015. Okay, so this is the one way, or we can write separately also. So you can do the shifting operation. So you can shift one bit to 0. So that means this is for the first bit set. Okay, left shift. Okay, so anything is wrong. Here we have actually mentioned 2. Okay, so this is the enabling for the A mode register, and similarly we will enable the clock for, so this is shift 2, 1, 2, yeah, sorry, 2. So how this is operation performing? So we are taking like this 0 0 0 0, and like last value is 1. So, and when we are using two left shifting, so this 1 is actually will shift at this point. Okay, so this will become 0. So now this bit will be set in our that register. So this is bitwise operation we are using directly on the register, and we are setting this value. So now this enable the RCC. This work is done, and now we will configure the mode, that GPIO mode registers as a input and output. So we have this GPIO mode here. So let's make comment configure GPIO A. Okay, so GPIO A is now configured as a output pin. So we will set this GPIO mode A, and we will perform so which bit we need to set. Okay, so GPIO mode IO will be set as a output. So let me move again. General purpose registers, and this one. Yeah. So you can see GPIO port is 9. So 9 mode means we need to set this 19 and 18 pin. This one. So this pin we need to set. So what we will do, we will perform the that 9 18, 18, and we will set the 1, and we set the 0. So 1 second, 3 1 1. GPIO. So output mode for this is 1. Okay. So output is this 0 1. So this is 0 1. This should be set. Okay. Yeah, fine, fine, fine. Okay. So what we will do first, we will that clean this bit. Okay. So we will just clear this bit. So how we can clear this bit 18 and 19? So to clear this bit, we will write a bitwise operation, that AND operation. So how we can clear this? So let me write the AND equal to, and we will use the that, that we want to clear 2 bits. So we will use the value 3. Okay, so this 3 value is representing 1 1 in the binary. Now we will shift this as a 18. Left shift as a 18. Sorry, 18. So that means this 1 1 value will be shifted to the 18th position. So that means 18th and 19th value will become 1 1. Now after converting this, so this is the left shifting, and then we will invert this, and we are inverting this by the this invert operator. So now this value will become a like this. So what we are doing in the left shifting first, so that value is looking like this. So 0 0 1 1 0 0 0 like this, and after inverting, all 0 will become 1, and this 18th and 19th value will become 0. So like this, okay, and all will become 1. Okay, like this. So just consider that this 0 and is the 18th, and this is the 19th bit. So in this way, this is working, and after that we will perform the AND operation. So you can see when we perform the AND operation, so the bits which we have currently in this GPIO mode register, so the corresponding 1 bit will remain same, that will not update by the AND operation, but 0 will become 0. So corresponding the 0 bits will become 0. So this is for the clear operation. After that, we want to convert only the 18th bit as a 1, because the 90th is already set to 0. So we will use the that OR operation. So that is so we will write OR operation equal to, and now we will do the 1, because we want to only set the 1 bit which is at 18th position. Okay, so in this two line, we are setting the 18th bit as a 1 and 19th bit as a 0. So this 0 1 is representing a value for output mode. Okay, so now port A is set to output mode by this calculation, and next is set configure the port GPIO port C as a input. So GPIO C mode register is this one. Okay, so this pointer we will update the value. So what we need to set this, so same register you can see 13. Okay, and we want to set this as a 0 0 input mode. So that means this bit 30 26 and the 27 should be set to 0 0. So to for this, so we will use the 3 to the similar calculation of the above. So this one.
Sir,
Hmm.
so
Yes,
totally how many bits are there here?
32, 0 to 31.
Oh, okay.
Okay,
And
each register have 4 bytes, and 4 bytes mean
okay.
32.
Yeah, yes. And sir, in the first one, RCC underscore ENR R operator is equal to the first one. Yeah,
Yes.
yes.
Hmm.
So the first, what's
So
the right hand side condition doing?
so what we have, the initial, suppose we have 32 bits, like the 1 2 3 4 5 6 7 8. Okay, so we have for each register we have 18 bits, sorry, 18, not 18, 32. So 8 8 8 8 like this. Okay, and what we want to do here, because the first bit, this bit is representing a port A clock, and
Yeah.
this bit is representing a port C clock. So this A, B, C, in this way port bits are actually arranged. So what we need to do, we want to enable the clock for port A and C. So that means this first bit should be 1 and this should be 1.
Yeah, yes, sir.
Okay, so we are setting this first bit by 1 by this OR operation.
Yeah, yes, sir. Yeah.
Okay, and this is the second. So 1 will be shifted to second bit, so this will also become 1.
Yeah, yes.
So both RCC will be enabled for both port. Okay,
So in the
now
first one, there is no shifting, right?
there is no shifting. 0, that means there is no shifting.
Yeah, yes.
So now this is the GPI C mode we have enabled as a output, and you can see we have set it the 26 and 27 bit as a 1 1. After that we have reflecting this that invert this, so it will become 0 0 at this position, and then we are performing AND operations. So corresponding all bit will become 0 at that point. So that will be considered as a input. So now this is set. After that we will use a while loop. So let's run a while loop 1. Okay, so this loop will run infinitely, and there's one more line, return 0. This is for int function. Okay, now inside this while function, so we will, what we need to do, we need to read the input from this port C, pin number 30. Okay, we will check what is the value at this location. Okay, the input data register. So this is the input data register for port C. So we will use this address and we will check what is the corresponding value at this point. So we will read the value inside this while loop. So we can take one integer variable int input equal to, and we will read the value of this. So also at this address we need to define the port. So our pin is actually 13, so we will write, so this is the base address, and we will use the AND operation to identify the value at the 13th bit. So we will use the AND operation. So AND equal to, and we will set this 1 left shift 13. Okay, so now we are reading this value. So what is the, okay, 1 second, we have done a mistake here. Okay, so you can see what we are doing, we are reading the value at this register at 13th bit. So 13th bit is reserved for 13 pin of port C. Okay, so we are performing AND operation of the corresponding 13 bit, and what will be the value if 0 is there, then 0 and 1 will be AND, it will become 0. If 1 is there, so 1 and 1 will be AND, then you will get 1. So from this we will get the value that okay, so yeah, this is the input we are reading from this pin. After that we will simply take the condition if input is equal to 0. Okay, so 0 means we are getting the 0 bit at the 13th pin. So what we will do, we will just output data register. So we will here update the output data register. So this is the output data register, and we will set this. So what we will do, we will perform the that. So yeah, we will make this output data register. If our input is 0, so that means output should also be 0 for the LED. So that means we will make as a 0 for this. So that means pin number 9 output we are taking from port A, 9th pin. So what we will do, we will perform AND operation, and equal to, and 9th pin. Okay, so 9th pin means, so we will take 1 and left shift 9. So now this is the pin we are updating, and okay, so we have to make 0. So we will just make invert. So that means this 9th pin will become 0, and we are performing AND operation. So this will reset. Actually, this will reset means 0. It will update the output data register to 0 at 9th pin, 9th bit. Else, if this is not 0, then what we will do, we will set this bit as a high. Okay, so this time OR operation to set, and ninth pin we will set to 1. Okay, so now this is the code you can see for the that input data register. So let's compile this and check is building or not. Okay, so yeah, so this is built successfully, no error in the code, but let's see it is working properly or not. So let's select the project and run STM32. So this is the first time, so just select as OK. Now you can see on the board, if you're able to see, the light is blinking. That means this is uploading on the board. Now this is uploaded. So let's check. Yeah. So you can see now on the board. Let me turn off the light. So you can see, I'm pressing the button, then it is turned on. LED, green LED is turned on the that breadboard. When I'm leaving this, it is off. Okay, so you can see this is working fine. When we are pressing the this push button, so we are getting in high input on the output data register, and our LED is now turned on. And when we are leaving this, now LED is turned off. So now this is the code for push pull LED input output. Okay, any query in this code? Anyone?
Sir,
Yes.
in line number 32,
Yeah, this one.
yeah, here whether the GPIOC underscore ID are getting updated.
No, it is not updating. This is a what we will get. So let's take this as a value. What we will get. So we are performing. Suppose I'm taking small example. Okay, for 8-bit. So like we have 0 1 0 1 0 0 0 1 2 3 4 5 6 0. Okay, and we want to find out that what is the seventh pin. This pin. What is the value of this pin? Okay, so what we will do, we will perform AND operation with 1 is shifted to that how many bits? One that this is 1 1 2 3
6.
4 5 6. Okay, 6. Okay, so 6-bit we will shift to this and perform the AND operation. So what value we will get for this? So this is 0 1 all 0, correct?
Yes, sir.
1 2 3 4 5 6 7 8. Okay, and we will perform the AND operation corresponding to this. So 0 1 0 0 0 0 0 0, and we are performing AND operation in these two values. So you can see if this bit is 1, so corresponding bit is 1, so you will get 0 1 0 0 0 0 0 0. Here we are not updating the value. You can see what is this operation? This operation is a input equal to. This is not a GPIO C IDR equal to. Okay, we are reading the value of GPIO this registers and we are performing the operation. We are not storing the result into the same register. Okay, that
So, sir,
output we are getting into the input.
okay.
Yeah. So one more thing. So this is not a zero, not equal to 0. You can see this is not equal to 0. Suppose what happened if this bit is a 0. This bit, okay. So you will get a answer 0 0 0 0 0 0 0 0 all 0 when you are performing AND operation. So 0 or 1 will become 0. So now this will become equal to a 0. So we are checking the condition. If we are getting 0, so that means this bit is set to 0. Otherwise, if we are not getting 0, that means this bit is set to high. So we will use that condition into the else mode. Okay. So here, if we are getting 0, so that means that input is low. So we will set our LED to low output. And if this is not 0, other than if we are getting any other value, that may be anything. Okay. So that is not actually 1. That will be some higher value. Okay, so the corresponding to the equivalent decimal value for this. So for this else condition, we are setting our output data registers to 1. So that means LED high. So now this loop is running infinitely on the board. When we are pressing our push button, so now this input actually become a high. We will get the different value because we are this update, this GPA, this value, this register will update actually. We are getting some input. So this will be update and we will get the different input in the while loop. At that time, our else condition will be executed. Or when we are leaving this, so our input will become 0 and that our this condition will be set execute. Okay.
Sir,
Hmm.
why we always use equal symbol after the AND operator?
This is a AND operation. Okay, you are saying this. Oh,
Yeah, it's like
this is
X
mistake.
with,
Sorry, yeah, correct.
yeah.
Yeah, let's update this. Yeah, this is not a correct way to write the code. Let's run again on the board. But yeah, board was working fine because yeah, if any, so that is actually become a assignment operator if we are putting this equals.
Yes.
Yeah,
So in the previous one, the GPIOC is was updated.
updated. Yes, correct, updated. Yeah, so now this is updated. Still, our board is working fine. You can see.
Yes.
Okay. So this is one experiment. Last time we have discussed the turn on the LED on discovery board. So same things you can do, but the discovery board actually direct have the STM pin name, but this contain the Arduino pin name. So that actually confused. So because of that, we need these two documents, that user manual for this your board and that reference manual. So user manual, you can see this pin connected diagram. So here you can find out the corresponding port. Okay, that what port actually you are using as a GPIO. So then you
Sir?
can write the code. Yeah.
So what's the name of the pins which are given on the outer region?
No, these pin black name, na? This one
Yeah.
are actually a pin name for the STM board. Okay, and
Okay.
because
Okay.
we can also connect this board to the Arduino board.
Okay.
So this blue pin is actually referring to the Arduino Uno pin.
Okay. So
And
it's
this blue one
Arduino
is,
equivalent.
yeah, so this blue one is given in the board itself. So this will become, you will become confused. So like this is given D8, but this is not a port D.
Yes.
Okay, so port is a port A.
Okay. Yes.
Okay, so because of that, just use this naming
Yes.
for STM, because we need to just if we are using reference manual, so all GPI port is name is given, so that you can extract the name. Okay.
And sir, why we didn't see any bouncing effect in pressing the push button this time?
What type of bouncing effect?
When we press the push buttons for turning on the LEDs.
No, why this effect? Because this push button is just connecting the that some voltage to the input pin. So that means that your pin input pin become high. When you are leaving this is disconnecting only. And this if you are talking about this pull up register and push down register thing, so that is already inbuilt in the circuit.
Okay.
Okay, so
Yes.
that is already inbuilt in the circuit, so you will not get any like any lower voltage if you are relieving this. So you will completely get the zero input if you are leaving this.
Yes, sir. But the bouncing effect, I mean, due to we are using the mechanical switches, there will be a slight bouncing kind of thing, right? Or
Uh,
will it be very negligible in this case?
this is negligible. I am so this is look working like as a switch. So when we're connecting, so I'm not getting actually bouncing effect. So what is actually that bouncing effect? I don't know. So this is related to the mechanical or what?
Yes, sir, the minute ups and downs the between the contacts of the push button.
So I think this is very negligible, maybe. So when we are
Okay.
connecting the switch, yeah, so that we are getting the input on the pin.
Yes, sir.
So maybe it is happening, but this is not. We can measure
Yeah,
it
yes.
this way. Okay.
Bouncing, sir, actually bouncing effect in work in when we program like toggling the LED
Toggling the LED. So toggling by the code or button.
by the code.
Okay. Then why bouncing effect in the toggling? Because
Because when we are pull down this GPIO pin and
okay.
then while loop searching for the next uh, state of the variable when we are storing the
Hmm.
value.
Okay, so by coding, if we are updating the register, so that will be read by the pin that what is the next
Right, sir,
value.
right now.
Okay, so maybe some, yeah, effect will be there, but here microcontrollers are designed in this way, so will not affect too much.
We also cannot eliminate this for including the delay around
Yeah,
20
yes.
milliseconds.
Okay, yeah, so delay we can give. Yeah, correct. So generally, when we are just using this toggling thing, so we generally give the delay. Otherwise, it will work like a always turning on because the clock speed is very high.
So I have another question. In
Hmm.
the embedded system, why not go to not suggest in implement in embedded system go to commands?
Which commands?
Go to in the C language go to.
Okay, you can use if you know about all the go to commands, so you can jump back. So this is a control statement now. So control statement you can
Yeah,
use.
control statement, but in the most of cases not recommended to use go to.
Okay, I also never use this go to actually. Uh, yeah, exact reason I also don't know what is this, why this is not recommended. But maybe I'll check this. Okay. So
Yes,
because
sir.
GoTo is also not too much popular in the normal C programming. Also, we never use this in the C as well as. But embedded C, if is there any specific purpose of this to jump? So GoTo is also work like as a we can jump at one state to another state directly if any condition is occur
Right, right, sir,
required,
right.
and we can define the that any level point. We define the level and then we can just directly go to that level, so we can jump back to the previous instruction and that or maybe next instruction, so that only manage the control of the execution. So where you find out this is not recommended?
From the seniors actually, sir. Seniors
Sir.
are suggest that you do not use go to in embedded C codes.
Okay, so have you used any time before this any C or anywhere?
I have done a lot of some NPTEL course in embedded
Okay,
system.
okay.
Sir,
Mm-hmm.
I remember the same from Nitin sir also in one of the lectures from C programming also in the first term.
Okay, he also mentioned that.
Yeah, yeah, yes, sir. But I don't remember the reason now.
Okay, I
But I
also not
remember
remembering.
one of the lectures he has mentioned the same.
Okay, I'll also
Just
check
just
this.
for 2 minutes. Yeah, small thing.
Okay, I'll
Yeah.
check this and will update you the next maybe. Okay. Okay. So this is the one experiment. Any other query or let's move to the next, the PWM, pulse
No,
width
no, sir.
modulus.
Move to PWM, sir.
Okay. So let's move to the PWM. So where PW, you know the concept of PWM, why we use this PWM or all these things.
Yes.
Pulse width modulation. So we can manage the pulse width and we can, based on that, we can also adjust the output, that output energy, or maybe we can adjust the brightness, we can adjust the speed, and we can also work like as a the digital to analog converter. Okay, so with the help of this PWM. Okay, so we will manage the width of the pulse, and by this modulation, and and I think you remember this one diagram. So let me just open this where professor have explained in week 4. Some code actually he mentioned that. Yeah, this one. So you know that we have some clock speed, that clock signal, that RCC clock that have some higher that clock cycles, like mega in the megahertz. So by default in this STM 16 megahertz is coming on the that output, or some timers like this. But if we want to set this, you can see this like high, low, high, this type. Okay, so this is very high speed, but we want to just control the that output, that based on the bit, pulse bit. Okay, so we want to manage the bit, like suppose if you want to manage the bits, this is for like this 500 microsecond second, and then low in this way. Okay, so this is like a up, and this is the on time, and this is the on time, and this is off time. Okay, and if suppose if we set this bit, so suppose if we set this up time for the largest time, and low time for the smaller time. Okay, like in this, and we pass this type of in pulse to the output. So what we will get? We will get the average. What is the average length? So this is more time to the high. Suppose this is 80% duty cycle. So 80% is high and 20% is low. So we will get the average something in way. So you will get the if you're connecting with this any output like device, motor, or something. So you will get a average output, average power output, that will become as a high. You will feel that you are getting high output. And same times if you just change the bit of this to the low, and like this, and on time is less and off time is high, like this. So suppose 20% duty cycle, so that means it will on only for 20% time. So you will get a low average output for this if it is continuously giving to the output. So this will work as a lower output. Okay, so suppose if you are getting output in like the first way, if you are in the LED is connected, so you will get the higher brightness, because the on time is high. And if you're getting this in type of input, you will get a lower brightness on the LED here, because this off time is high. So in this way, if you can manage this bit, if you can change this bit, so you can also that handle the power on the output. Okay, and you can adjust this output based on this bit of the pulse. So that things we can use to manage this adjust of brightness of the LED, or motor speed, or any other application is also there. But these are the primary application where we can use this to manage the output power. And we can replace this by this way we can skip the use of that A to that, not A to D to A converter, digital to analog converter, where we are getting the analog output like this. Okay, so high and low. Okay, so we can also perform that task with the help of this PWM, pulse width modulation. So this is one purpose, and some setup is required to perform this, so that we will see. And our code is actually to adjust the brightness of the LED with the help of this. So we will update this PWM width, and this part is actually discussed in the week 4, that PWM lecture. So this is some setup required, and we will use the timer. So initially we have some higher clock speed, but we will use the timer, and we will just set our timer in this way. So, and we will use our timer as a output clock. Okay, so that output clock. That means, and this timer will work like as you suppose this pre-scaler and period, this value is given. So how this will work as a, so pre-scaler means, so it will reduce the cycle count by the division of this operation. So suppose if you have 16 megahertz frequency, so like 10 to the power 6, and you will divide this frequency by first 16, and you will get a 1 megahertz. And after that you will also divide. So this is the calculation. Timer count for 1 kilohertz is equal to 16,000, 16 megahertz by this 1000 hertz. So basically we want to convert this higher frequency to a smaller, that 1 kilohertz rate. So because of that, we are using this pre-scaler to reduce the cycle count, and we will use this period. So for one period for the timer, so that means 1000 cycle of the our input clock. 1000 cycle will be our timer will consider as a not, yeah, that one cycle actually for the timer will like work as a this. If we set our uh, duty cycle as a 50%, so this means the period of this will work as a 1000 k kilohertz. So that means 500. If you convert this kilohertz into the time, so that means some microsecond. So you will get as a like 500 microsecond for that higher timer input, and 500 microsecond for lower input. If our duty cycle is 50, okay, 50%. And if we change this duty cycle to 500, that's 50%. So that means if we change this to 200, okay, so this will become as a we have total cycle 1000 for one time, okay, timing position, that means high. So that means clock cycle is like will work as a this type of clock cycle 1000 cycle. Then your one clock cycle will be completed by the timer, high input, and one for the low, 500 and 500. Okay, if you change this duty cycle to low, so let's suppose if you change this to 200, so this 200 cycles will be convert as a high input, and 800 cycle will be converted as a low input. Okay, so your pulse cycle will become like this. Okay, so low is the for the 20% time, and 80% time is it will become a low. High will become a 20%. So based on this duty cycle, you can update the that width of the pulse. Okay, and pulse we are getting from the timer. So timer is just a counting the cycle of our input kilohertz. So after 500 cycle, it will reset to 0, and then after 500 cycle, it will increase to 1. In this way, our timer will generate a pulse width modulation, that clocks. Okay, and we will feel that our that if we will change this bit continuously by the code, then we will feel that our output level overall average actually will be updated, that output power average will be updated, and accordingly our led brightness will also be changed. Okay, so these are some concept, and you can see the lecture for this for the more detail. What is this PWM, and what are the application for this? And here for code, we have connection. We have the same type of connection. We have already connected this LED. Okay, so now we will use the timer code for this. So now this is the code, and let's run the another project file. Open new STM32, and so board, let me P4G 74RE, and this is the board. Next, so same things, we will give the nucleo PWM LED. Okay, and empty project will start. Finish.
Sir,
Yes.
Are you using a different application?
No, I'm not using. I'm using the same that QID STM32 QID.
Okay, yeah, yeah. So it's not a walkway, right?
No, it's not a walkway. Yeah,
Okay, yes.
yeah. This is direct hardware. Actually, we are using physical hardware, no.
Yeah, okay, okay, yeah,
So
yes.
because of that,
Correct,
we are
yeah, okay,
using.
yeah, yes.
Okay. So here we have this. Uh, this is the previous code. Or this is the, this is the previous. But we have opened the register. Okay, we have to open this. Let's close this. This one. Okay. So same things we will do. We will figure out that which output we will use for the LED, which pin we will use for the LED, and here we will only use the output pin. We are not using any input things, so we will only focus on the output. Yeah, one more things we have to figure out. Uh, one sec. So that configuration we have to understand that which actually timer is connected for which pin. So let's say I'm creating one new project, so we can see that configuration. So this is only for the pin configuration. So selector, same things, nucleo, G4. Okay, so I'm this time I'm not connecting this empty. Okay, I'm giving some name PWM demo. Hmm. So you can see when we are opening the project in this way, so we can manually configure the pins directly. Okay, so this is the microcontroller pin name. Okay, so that is actually we have. So there you can see the port PA6, PA7. So that is representing port A6 direct microcontroller pin structure. And here we can configure any pin as a LED that output. So suppose this PA5. Okay, this PA5 pin is connected as a green LED on the board itself. So we have one user LED on the board itself, and same things we can also use this as a output pin, and we can connect our output pin on this pin. Okay, so this PA5, and when we click on this, we can see here some timer is also there for this pin. Okay, so tim2 channel 1. So this we will use this timer to channel 1 pin as a we will use this timer for this pin for a PWM purpose generation. Okay, so timer 2 ch1, this we remember that. uh, and after that we will configure some settings. So you can also do the coding in this way directly by manual this. So just configure as a pin in a input and output mode, and you can just set all the settings from directly here, and you can generate the code. After when you will save the code, the code will be generated, but that code will be actually a that HCL code, hardware abstract code, where the many abstraction is there. That will not be the register level code. Okay. So all configuration will be provided by this IDE directly. You need to write only that specific while loop code. All this registered value, that pin set, all these things will be done by this IDE. Okay. So, but here we are only using this information that if we want to use this board LED, PA5. So what timer is actually connected for this? So this is timer to channel 1. Okay, time to channel 1. So go to the our main file and just look this that pin diagram. So that PA5, so PA5 is connected to where, sorry, what's is given, let me this PA5, okay. And PA5, can you see this PA5 is, yeah, PA5 is connected to D13 in the board. Actually, this board pin name is D13. So D13 is just a pin of the below than ground. Okay, so I am connecting that pin our board, so to 13, and yeah, so this and the same LED will also be turned on the board, and we have also connected on our breadboard. So both LED will be reflected. And this is the board, and we will use the timer 2 for this. So let's just get all the details of this base address. So what are the base address required? We need to find out the RCC address, and this time we have two peripheral. So one is port, GPIO port, okay, and another is we have timer, okay, timer 2. So GPIO port are connected AHP2 bus, and the timer 2 is connected with APB1 bus. So let's see, you can see the document and that system memory, and you can see this. Okay. So GPIO port AHP2 bus and that timer 1. Okay, so timer, you can see, yeah, timer 2 is connected to APB1 bus, this APB1 bus. So we need to enable the clock for these two bus, that, okay, that one is for timer 2, another is for GPIO A port. So first we will figure out the base address for this, base address for port A, and we will write the address. And in this code we need to set many setting more that for the timer configuration. So that we will do, yeah, this is this main. Okay, so let's define some address. So has define that RCC for that port. Okay, so port A. Okay, and same things we will write down the similar address. What was the previous file? Let me go code from that. So yeah, in this way we'll use, so GPIO port A, I am directly copying this. This line we can directly use. Okay, and RCC port A. Okay, so we need the address of RCC. So port A RCC, this one. Now RCC timer. So I am writing the RCC timer. So time TIM2. Okay, so we will check what is the address of the TIM2 RCC. We have to check this. And GPIO A mode, this mode register, and we will use this as the output. So this is fine. So let's check the timer register. Okay, address of timer register. So this is, go to this. We have this now. Time to base address. TIM2. Yeah, this is the base address we will directly use. One second. APB1, PP1. This is the first. Okay, so let's open this register. Let's see. Into APV1, this one. Do you have any other register? Team 1. Team 2. Okay. Okay, so let's move to this register, timer register. RCC is the RCC reset clock cycle, RCC register, and here we have some peripheral type APV1. So here you can see this 58. This is the APV1 peripheral clock enable register, and this is you can see TIM2, TIM3, TIM4, all these registers we have. So we will use this as a 58, and 58 we will use the in the address. 58. One second. PP1. TIM2. Okay. Yeah, this is fine. Okay, so this two address we have now noted down, and above one is noted down, that GPIO mode register. So this is the GPIO mode register we will do in the same way. Here we have also need the address for other things. Okay, so first things we will check GPIO A mode register. So first we will enable this timers for these two timers in the code. So let's enable the clock. So enable the clock for port and timer. Let's open this PWM bit. Team 2 channel 1. Okay. So what we will, how to enable this? So now this is the first. Or operation equal to, and this is the base address to RCC clock. So first is mode HB1, HB2 for enable register. So these things, because we need to enable this first bit, okay, GPIO mode A enable. So we will only perform the OR operation between this OR. Okay, so like this 1 and left shift 0. Okay, so this is the first GPIO port A, and Okay, wait, this is showing error. This should be close here. Oh, sorry, equal sign. So, okay, this is the first one, and then RCC time 2. This we will also update that all operation equal to, and let's see what is the timer for this. AP1 peripheral clock enable register 2.
Google search.
So this one you can see the first bit is representing to the timer 1. Okay, so timer 2, sorry, that we want to enable. So that means we need to set only the first bit the same way. Okay. So now this is to
bracket.
So now our clock is enabled. After that, we will set our GPIO port mode. Okay. So set GPIO is, and we will configure this as not a input or output. We will configure this as a another function. So that if I am writing another function, so how we will just enable this. So this is the GPIO mode register, and inside this GPIO mode registered. So let's move to this GPIO mode. Okay, all these are registered actually. Yeah, mode this one. Okay, so in this time, because we want to perform some other operation, we are not performing that input things and output things here. This time our output will change, and we want to use this our output as a that RCC, that clock output. So we will use this uh, alternate function mode. Okay, that means we will use high and low alternate output as a pulse in the, okay, in the output pin. So we will set our pin as a 1 0 for this. Okay. At our GPIO port A. So 1 0 means our port output port is now that pin. Forgot that. This is port A. What was the pin? PF5. Okay, so PF5. Yeah. So 5, we need to set our pin 5 as a the alternate function mode. So here, so now how we will set this mode? Uh, 5 as a 1 0. So to set as a 1 0, what we will do? So we need to set 2 pin for this. Mode 5 is this one, this one. That means bit number 10 as a 0 and 11 is a 1. We need to set this. So how we can do this? What we can do, we can clear this bits first. So that means we can shift our 1 to that at that 11 level, okay, 11 level. So that we will change, and equal to that invert. Okay, so invert, and that 11 3 11 time. Okay, so this is for clear bit. So this clear bit means so that sorry, 10 times, not 11. So all will be all 2 bits will be clear. So this is equivalent to 1 in binary. So we will set 10th and 11 bit to 0 by this operation. After that, we will set our 11th bit as a 1. So that means we will perform the operation, that set operation to 11, and only this is only 1. So in this way, we have set it our pin as a alternate function mode. So now this is the one, and after that we will take our register address for alternate function. So in the same list, you can move to lower side, and we will use this register. That GPI port configuration lock register, alternate function low register. Yeah, this register. Okay, and here the offset is 20. So for this registers, we will use the base address of the port A, and then we will add this. So we will use the another address here, and this is other function, that alternate function. So A F alternate function registers. So and this time this will become 20. So now this is the alternate function register. So now we will set this value to AF1. So AF1 is basically for the timer 2. So because of that, we will set to this register. Okay, so what we need to put the value. So this is our port 5th, and for this we need to set 4 value. So 4 value means we need to set our registers for this AF1. So AF1 is actually for timer 2. This is okay. So now we will set our 0001. So that means what is the first bit? 5 is 20. 20 bit we want to set as a 1, and remaining are this 4 bits will become 0. So what we can do, we can first clear the bits. All 4 bits we will clear this. After that, we will set this 20 bit to the 1. So we will update this. Yeah. So now this CPIO ARL. First we will clear this. So for clear this, we will use this type of operation. And this time we will use 15. So 15 have the 1111 in the binary equivalent. And we will shift this to 20 value. So it will become from 20, 21, 22, 23 like this, all will become 0 by this. After that, we will set our 20th bit to that 1. So this is now 1. Okay, so in this way, now our bit is set to this 20th. Okay, so 20 10. This is fine. So now this will become set as a this one 0001. So now this is done. And now next thing is now the next thing is timer configuration. So we have many things for the configuration is timer. So we will set the prescaler value, and here we will understand this. We are supposing configure on the manual things. So it's still suppose we want to configure this PF5 this pin as a that time to CH1. So you can see this is showing yellow, but after that we have to set many things in the time to by this. So you have to enable the clock source internal clock, okay, and you have to set the channel 1 as a that PWM generation channel 1 like this, and after that you have to set that prescaler value. So generation PWM, okay, and also other setting you have to do. You have to set some prescaler value. Suppose if you are selecting 15, so that value will be converted into it that divided by 15 plus 1. Okay, so that information are given in the register, all the registers thing. So if we want to do set this all setting for this timer, so we have to use the registers for that. So we have many registers here. We can do all these things manually. We can put all this ARR value. So what is the total clock cycle value, that cycles value for one timer clock. Okay, so that we can set. So these things we can set manually here, but for the register level we have to set all the registers value. So for these things we will set all registers address. So what registers we need to for this code? So first we will read the timer 2. So we have GPIO timer, that not peripheral timer. Okay, so let's check. Yeah, you can see general purpose timers. Okay, so for this we have all the details, but here we have registers from this point. So now there are many registers, and we will use many among of these registers to set our TM2 channel 1 as a that PWM mode. Okay, so these are some registers we have. So let's set this. You can see this document to understand all the working. So I'm just writing some registers value, and we will check the base address for that. Okay, so first we will define that. So I'm writing timer 2. So TIM2, that control register. So first is the control register. So I am using CR control registers 1, and we will define some base address for that. So each registers have some address. So we need to assign the value for that. Okay, so this is for control register. This value we will change. Okay, so I am writing 000 here. Yes. Similarly, we will assign all the time. So one for pre-scaler we have to define. So pre-scaler we will define like time to PSC. Pre-scaler, so PSC we have to define, and one for that that reload register. So that we have to set this. You can see these things. So we have to set this time pre-scaler value, time period. So this is basically called as a auto reload register. So that value we have to assign. So period for 1 kilohertz frequency. So and timer compare, that means duty cycle. This mode we have to enable. Okay, so which mode we want to use that timer? So PWM mode we want to use. We have to set this. We have to start the timer, enable the timer. So all these things we have to set by the timer configuration. So I'm writing the registers name in the code. So PCS is for the pre-scaler, and after that we have one for the auto reload. So ARR I am writing. Okay. And another we have some compare register, that compare enable. Writing. So you have C. So I'll explain that what is the meaning of each. So one is CCR. CAR. And one we have for CCR1. 1, 2, 3, 4, 5, 6. So these many settings we have to do. So what is the meaning for each? So this TIM2 is basically a pre-scaler. Okay, so this is for pre-scaler. So pre-scaler setting. The second is time to PSC. No, that one. That above one is the control. Control register. The second one is the pre-scaler. Okay. And third one is the auto reload value. So that auto and CCMR. So this is CCMR one is just selecting for that register as a which mode actually which mode we want to use this. So that is we have to use for mode that we will select as a PWM mode one PWM, and this one is for capturing or compare one output CCER. So capturing the output compare. And last one is the CCR that duty cycle. So this is for the duty cycle. So these we have defined. So these six value we need to define as a configuration for the timer. So first things we need to identify the base address for all. So address for the first thing timer that C TIM2 that we will check the address. So timers document we will move timer base address. So base address is this one. Where are the timer compressors? Okay, this one. Yeah, so this is the registers. So you can see this TIM2, this is coming in this, and we have this register. So offset, first this timer control registers we have. So offset is 0. So we will use the base address for the timer 2 for this. So that means you will set the address. So what is the address for base timer 2? Let it RCC clock. Okay, so base address we have to copy. Second. Oh, okay. RCC we have, yeah, this address we have marked incorrect. Sorry. Oh, base address was 00. This is for timer.
You put this in there.
So this address will be used for the timer clock register. But yeah, this is RCC TIM2. So that we have to check the RCC TIM2. So RCC base address is this one. So that we found wrong. You can see RCC registers was this one. RCC base address is this one. Okay, so this is the base address for RCC, and 58 we will add as a offset for timer. So this is the okay. Now this is the address of timer base address timer 2. Now because the offset is 0 for control registers, we will use this. After that we will check the address for that pre-scaler value. So pre-scaler address is up to the same. So in this pre-scaler, you can see just move to all this. So compare, capture that pre-scaler, this one. Okay, 28 is the offset for this. Okay, so in this way you can figure out all the address by this register. So that means this will be the base address, and you need to add all the address in this. So that means this is 400, this is 28. Okay, the next is ARR. So ARR registers we have. times ARR. Auto reload register. So 3 and 4, and this is the X2. So timer 2, this is the one. So 0 2C. Okay, so 2C we will add in this base. So this is ARR 2C. Next is that CCMR1. So we have the CCMR1. CCMR1 capture here, this one. This is 2 to 5. So 18. And CCER. CCER, we have CCER, this one. Okay, so this 20. Now CCR1. So CCR1. CCR1, CCR2, CCR1, this one. 3, 4, 2, 5, 34. So 34 is the this one. So now this is the address registers for all registers of the timer 2, which we need require. So now we need to just set the value for these timer registers. So pre-scalar value. So we will do configure the timers. So that means configure the timer. Okay. A pre-scalar value we will set to 15. So 15, if you are setting 15, so it will be divided by actually 15 plus 1. So that we can directly assign. So 15. Okay, so that will be assigned directly. So and another is auto reload, that registers we will directly assign to 999. So that will be divided by that plus 1000. So this one. And yeah, this one. And that duty cycle we will also use only 500 initially, and we will update this in our code. That duty cycle means that it will actually update the width, so that we will use 500 initially. Okay, apart from the other registers we have to set some value, so that we have to set in PWM mode. So like this CCMR1, so that we have to set this. So let's open the register CCRM1. Yeah. So in this actually we will set this this value. This is CRM2. Yeah. First we need to set preload. This bit we have also need to set that enable. We have to enable this output compare one preload register. That we have to enable this, as well as we have to set this PWM mode 1. Okay, so 1100. So these two value we need to set in this register. PWM mode 1, PWM mode 1, yeah. One second. This is not correct. No, this we need to update. Yeah. PWM mode 1, 0110. So, and this is the bit numbers 4 to 6. So 4 to 6 we need to set this 110. So how we will do? We will update this. First we will reset this to 0. How we can do this by the same operation and or and. So we want to set that 7 it is 111. If we set 7 left register and 4, and this is okay. So now this is a 7 is 111, and it will actually, sorry, it will actually reset the value of this after 4 5 6, that value it will reset. After that we will update that value by uh, 0110. So that means OR operation, and that will be a 6. Okay, yes, 6 is 110, so that will be updated. So 4th bit will be set to 110. Okay, so this is clear and this is update. So, and apart from that we have to set one more bit from this, so that is actually to enable. So that timer, directly set this. So that is third bit actually. So 1 is less than 3. So this is for that option. This one, yeah, this one bit 3 actually. This we will select for the compare one preload enable. So we will update enable this. And apart from that we have two more so registers. So first is, now this is updated, CCR1 AR PCSA control registers we need to enable. This is the first registered actually. So that first registered we have to, okay, 1 second. This is the first control register. So this one actually we have to set that see capturing one. We have another version of STM or control register too. Direct CMS. Oh, which bit is actually read to subtract? Yeah. So this CEN first bit 13 13. Okay, yeah, so we have to just enable this counter enable. Yeah, counter we have to enable. So 0 bit we have to set. Only we can do set this 0. Now this is done. This is remaining. CMR1 is done. CCER is done. Done. Yeah, this one CC. So CCER will also be enabled first register CC. This one. So here also we need to set this 0th bit to capture mode enable. Okay, so same things we will do with this. Okay, so now all these configuration are required. Just go visit by the registers details. So what are the actual purpose all these things? So some are actually very clear, but some are actually a little bit setting required for this output channel. So now this is done, and after that we will do the code for that change the duty cycle. So we will only update the duty cycle, and that duty cycle will be updated, and our code will work fine. So one. So inside this, we will set what we can do. We can also make a delay loop. So what we can do, we can define some functions. So diff and delay, and not diff, sorry, that void. Okay, and we will just take this delay. And somewhere to we will take here, so and we are running some loop. So while at n minus minus. So this we are delaying some. We will give some delay using this while loop. So if we suppose v was 10,000, so this loop will run 10,000 times. Okay, and after that we terminate. So this function we will call as a delay function, and after also we will write a function one for setting a that duty cycle. So we will change the duty cycle in the loop, and we will set that duty cycle. So that void set duty cycle, and we will pass the int duty some value. So now this, and inside this, if our duty is less than equal to, so 1000 we are taking as a maximum range from 0 to 0, and then we will set our duty that time, that CCR1. So this is for duty cycles. We will set our this. Okay, now inside the main function we will run a loop. So for int I, or we can take anything. So int I will start from 0, and I is less than equal to 1000, and I plus plus. Okay, so this I value we will use as a duty. So now this we will set, we will call this our function set duty. Yeah, and we will pass the I value here, and we will also call some delay for this. So while delay, so we will pass some value like 50,000.
Sir,
Yes.
why we have taken 1000 as a maximum limit for duty?
So duty, actually we have the range for that means for one timer cycle we have the 1000 clock cycle, that we have scale that na. So 16 megahertz we have the input frequency. After that we are dividing that frequency by 16, and that we are converting that into a 1000 cycle.
Yeah.
Okay, so
Right.
here duty cycle we are taking 50% initially.
Okay.
So this duty cycle we are changing. We will change from 0 to 1000. So
Okay.
if it is 100, that means 10% on.
Okay, sir.
Okay, so in this way we will just update this duty cycle from 0 to 1000 value.
Oh, yes, sir. Yes.
Okay, so this is now increasing duty cycle. After that we will decrease the duty cycle. So that we will start from 1000.
So, sir, it's instead of duty cycle, we can call it as on time, right?
You can take, so duty cycle means is also same on time in percentage.
Yeah. But when we say duty cycle, it usually goes from 0 to 100 percentage.
So here actually this duty cycle we are using as a value
Oh,
from
okay.
0 to, but by default
Okay.
this will work as a in the that percentage.
Okay, okay, sir. Yeah.
Okay, so we are taking this duty cycle range is 1000,
Okay.
and if we are giving half of them, it will work as a 50%.
Yes, sir.
Okay, so now this is the another loop we have to reducing the, this is the increasing duty cycle, and now this is the that decreasing duty cycle. So 1000 to so 0. Okay, so that is, yeah, we can take less than or equal to, okay. And I minus minus, and we will pass this and we will perform this. Okay, yeah, so this is the while loop. So in this way we have this code. Sure, this is becoming very long. Let's check. PWM LED. Okay, build is fine. That run. Okay, so now on the board you can see, let me see here. Just see the board LED. Okay, so that it will increase and it will decrease. So this. Uh, oh, I think it is increased to high, but it is not reducing. Okay. Okay, so I think we are reducing by one. So because of that, it is running very late. Yeah, it is reducing. So, but it is running very slowly. So let's make this I plus equal to like 10 minus equal to 10. Sorry. Because it is increasing, we are also giving the delay, na? So it is reducing very slow. Let's change this. Build project and run this again. Now you can see this brightness is now controlling. So it is high increasing and it is decreasing. And same time on the board also. So board you can also see one that, if you see, let's see night. There is one green LED also there on the blue, near to blue switch. So that is also connected on the same pin. So because of that, that is also reflecting that brightness. Okay, so in this way, this PWM is working. We are able to adjust the brightness based on the width of this. Okay, so you can increase the speed or decrease the speed. Okay, so by the selecting of this duty cycle, that suppose if I reduce this 10 or like 20, it will be flag. PWM LED. Okay. Build project. Run STM 32. Okay. Now you can see the speed is increased, that up and down. So we can use this to adjust the motor speed or that things we can also use for this PWM. Okay, so you can try this if you have board. And you can also try this on the that walkthrough also. That walkthrough you can also create the C based code. You can create a C file. Okay, any query in this?
Sir, you could can you share the code in the chat box so I can modify
Okay,
accordingly to my board?
okay. I'm saying 1 second. So this is for PWM, and the previous one. I think in one time it is not come. 1 second. So let me check where it is cropped. So define TM to CCR1. Okay. So it is not coming in the one way. Okay, I'll copy on the discourse. Can you copy from there?
Okay. Okay,
Okay,
sir.
so because it is not coming, we have to copy many times.
Sir, another question I have.
Hmm.
In this course, I basically introduce the concept of embedded C and the STM32 ARM architecture is a part of the course.
Hmm.
So, could you please suggest any document which I have learned about the architecture of STM32?
No, actually, this course is not directly based on this STMR32 because professor have taken this as a one board, but professor is explaining all about the concept of this that embedded system. Okay, so because of that, we are also discussing this register level programming because it may be changed on the board wise. So maybe that STM32 is used some another that HAL another type of coding. So another maybe another board maybe also can have the different types of some coding. So professor is only explaining the concept of that
Embedded
embedded
C.
system, not C,
Okay.
embedded system.
Okay.
Okay, but we are taking the example that in the C, why the that hardware level coding is better than the abstract layer coding. So we will take some example time to time, and professor will also explain something in later week.
Okay. Thank you.
Okay, this is more about the general course, not specific for STM. Okay, yeah, Muthu.
Sir, in
Yes,
the initial lines,
of the code.
yeah, yes, sir.
Mhm.
So, are we typecasting the pointers?
Yes, we are typecasting. No? So this address we are directly taken from the document. Okay,
Okay, yes, yeah,
and
yes.
this address is representing a that we are converting that address into a one integer pointer.
Yeah, okay.
Okay, and we are assigning this pointer value using this macro.
Oh, okay. Okay.
Okay, so at any time if we are using this name RCC this, so that will be considered as this address.
Okay.
Okay, and you can also
So,
define, so this is like a macro, but you can also define as a variable inside the main function.
so
Okay, you can just assign directly.
yeah, yes, sir. So, what's the reason we are typecasting it into int star before taking its value?
Because we want to access the we are converting that into a int asterisk. Okay, so that means we want to access the 32 bits for that. So int is taking as a 4 byte. Okay,
Okay.
so int is taking 4 byte, so 4 byte will be, that means 32 bits, and each
Yeah.
register size is 32 bits,
Okay.
and we want to access each bits by this pointer address. So because of that we converted into int, and this int is not a correct way. We will use that uint, that uint 32,
Yeah.
because yeah, okay, so that is also one important thing. You can change this that uint and 32. So we have this now 32 underscore t. uh, that is uint 32, that is defined now. Okay, 32 underscore t. This is not coming. Yeah, but we will use this type of, okay, so integer is also working fine, but generally use this stdi int dot h, that type. So this will we work similar to the all type of compiler or all these things. You will always get the 32 bits for
Yes.
that typecasting. Use that. Okay.
Sir,
Yes.
I have one doubt in week 4 grade assignment.
Okay, one second. B4 grade assignment.
Last question.
This one. This one.
Yes.
Okay.
So, yes, sir. So, both option 2 and 3 can be a correct answer, right?
No, all are the application of this. This last one is also the application of this. Okay,
Yeah.
we perform the signal, digital signal to analog signal also. We can also do this. But the what are the primary purpose actually is to just manage the power of this, that power of the output. Okay, so that we generally use to manage this LEDs and motors by this adjusting adjust the power, the output. So this is the primary purpose actually. Okay, and it is discussed in the lecture also. It is a common purpose for this. So this is because of that. This is the answer.
Yes, sir. But when we do, I mean, when we control the brightness of LED and speed of motor,
Hmm.
anyhow, we are converting the digital signal to analog signal, right? Using PWM.
So but no, that is a application. Digital signal to analog signal. Yeah, we are doing this. Okay. So to control the brightness of LEDs and the speed motors and generate high frequency signal for communication. You are saying, yeah, this is also incorrect. Yeah. Okay. So this is not re-evaluated.
No, sir.
Okay.
Some other two questions. I think 6 or 7. I'm not sure. Those are re-evaluated.
Okay. Okay. This is now zero. Okay. Yeah. Primary purpose, and I'm remembering in the lecture actually, professor had explained that this is the primary purpose. One second. That PWM, no? Hmm. Applications. So LED brightness, motor speed, power delivery, and communication. Generic. Okay. Okay, so yeah, that is correct. So I'll check this. Okay, and maybe we will reevaluate this also. Okay, so
Yeah.
I'll
Yes.
discuss this with team and that I'll check and we'll give the marks maybe for all.
Yes, sir. Yes. Thank you, sir.
Okay. Okay, then any other no query, then we can close. Yeah. Thanks everyone.
Yes, sir. Thank you, sir. Good night.
Thank you.
Good night.